Good morning, good afternoon, good evening, depending upon where you're joining us from. I'm Ira Feldman. I'm the MEPTEC Executive Director and would like to welcome you to today's MEPTEC IMAPS Semiconductor Industry Speaker Series. So thank you for joining us. Our next Semiconductor Industry Speaker Series will be our traditional, or our now traditional holiday hangout, December 15th. So it will be on a platform where we can all just communicate and say hello to people we've missed in the last year, and just connect up. So we will send out a link to register for it. So please drop into our holiday hangout December 15th, starting at 11:30 a.m. Pacific time. It will be live. We will not be recording it, but please join us and say hello. We look forward to seeing you there. And then we will also be announcing the Semiconductor Industry Speaker Series for next year as we confirm presenters. And if you're interested in speaking at one of the webinars or luncheons when we resume them early next year, please let me know and we'll work to get you scheduled. And we're always looking for new presentations on interesting and relevant topics. So thank you. About MEPTEC, we are a member-supported organization. A number of your memberships renew in December, so you'll be getting an email. But if you're not a member, please consider joining, as it helps support our activities, and it also provides you copies of the MEPTEC report. And we're also welcoming corporate sponsors. So if you're interested about joining, renewing, or sponsoring, please reach out to Betty, bcooper@meptec.org, and she can fill you in on the details. Okay, and with that, it is my great pleasure to welcome to today's Semiconductor Industry Speakers Series, Dongkai Shangguan, who's going to talk about machine language artificial intelligence, a critical enabler for advanced semiconductor packaging and electronics manufacturing. Dongkai works advising several innovative companies in the global electronics industry, and currently he is serving as a VP at Adaptix. Previously, he was corporate vice president for advanced microelectronics and manufacturing engineering at Flextronics, now Flex, and as the chief marketing officer at Stats ChipPack. He's also worked at other companies such as Ford Motor Company and Visteon. He is an IEEE fellow and an IMAPS fellow. And with that, I would like to welcome Dongkai.
Thank you, Ira, for the introduction. I want to thank everyone for taking the time to join the webinar today. I see there are already close to 60 people still growing. I'm delighted to have this opportunity today to present on machine learning and AI for advanced semiconductor packaging and electronics manufacturing. So over the next half an hour or so, I'll begin by a very brief overview of the technology trend for advanced packaging, followed by a brief introduction of machine learning and AI, and the architecture of machine learning AI platform. I'll spend most of the time sharing a few use cases and applications to illustrate how machine learning and AI can be leveraged for semiconductor manufacturing and packaging, advanced packaging processes. I know here today we have many experts in semiconductor packaging and electronics manufacturing. We heard a lot about machine learning and AI, but how can we utilize this new tool for the work we do? So I hope to use some use cases to illustrate that. Then finally, we'll summarize with time for Q&A. So advanced packaging, we all know very well, a lot of new technologies, new innovation. One of the key trends, at least from my point of view, is miniaturization. I have spent a lot of time on miniaturization, and many of you have as well. And to achieve higher functional density through finer pitch, 2.5D, 3D, chiplets, heterogeneous integration, etc. And then in the business and the operation space, so what is important, as we all know, is one is high throughput, because we're using very expensive equipment and we have a capacity constraint for high volume production. So throughput, cycle time throughput is very important. Then yield is very important because we are dealing with very demanding, challenging processes. And also the chip and the system are very expensive, so yield is also very important. So all of this lead to lower cost and fast time to market, right, for different applications, high speed transceiver, autonomous driving, and 5G and so on. So we all know this very well, but my message is machine learning and AI can be utilized, leveraged to help enable many of these aspects, enable new innovation. That's my key message for the talk today. For example, if you look at the advanced packaging, right, one of the key requirements in terms of process is precision alignment, for whether it's for transceiver, for image sensor, LED, MEMS, LiDAR, or for fan-out, 2.5D, 3D chiplets. As for transceiver, for example, I just attended a seminar a couple of weeks ago here that talk about photonics. The precision alignment is so critical for the performance of silicon photonics, right? Submicron alignment accuracy. Then for advanced packaging, if we look at where the industry is going, we'll talk about 10 micrometer pitch or even less. Then because of that, the alignment accuracy typically is 1/10 of the pitch. Right? So if you look at what happens over the years, what has evolved over the years, and many of us here today have been with the industry for many years, and if you look at the alignment accuracy, has gone from 100 micrometer then to 10 micrometer, and today and where it's going to 1 micrometer and below. Hybrid bonding, for example, chiplets are going to demand a very, very high alignment accuracy. And if you look at the method, it has gone from passive alignment to active alignment. But what I'm saying is to meet the challenge of the 1 micrometer, sub-micrometer alignment accuracy, machine learning and AI will be very critical. So because if you look at where we are today in the industry, if you look at die bonding below 10 micrometer pitch, it's very challenging. It can be done, and but it's not so commonplace, and it's a challenging process we all recognize. And also, we also have seen that there is often a trade-off between the cycle time and the alignment accuracy. Often we have to slow down the machine. But the problem is we cannot afford to slow down the machine because we have a capacity constraint in the industry, as we all have seen. Right? So how can we achieve the alignment accuracy and also with the throughput with the short cycle time? Right? And so all of this will lead to yield and cost and time to market and meet the demands of the industry. Right? So machine learning and AI. So what is machine learning and AI? Today we're not a seminar just talk about machine learning and AI, but just briefly, machine learning is an AI subcategory, and it's a focus on finding patterns in data, data analytics, finding the pattern, then use those patterns to make predictions. And once we can make predictions, then there are a lot of things we can do with that prediction to guide our processes, our machine. And there are many methods of machine learning, and I'm sure you have heard, and you can learn more. There's supervised learning, mainly for classification and regression. I think we're all very familiar with the regression. We have done many of us have done regression before, but this is much more sophisticated. Right? But then also very importantly, unsupervised learning. So the machine The algorithm is identifying the pattern in the data itself without human intervention, because we do not know what relationship there might be in that data. The machine's doing, the algorithm doing that, unsupervised learning or clustering, association, etc. But often in real work, it's a combination of both, right? So when I first heard about machine learning, I thought, oh, machine learning is just a DOE. We have done DOEs before. I have done a lot of DOEs, and many of you have done DOEs. I thought, okay, just a sophisticated DOE. But the more I know about machine learning, the more I realize that it is, I would say, infinitely more powerful than the DOEs I have done, especially in those cases I listed here. One, it can deal with multivariate data, 360-degree view. What that means is, for the example I'm going to introduce, it's utilizing the machine sensor data as the machine is running, and as well as data in the process log. Some of it is the contextual, and it's also utilizing the machine top level data, for example, alignment accuracy and epoxy dispensing area, as well as line level data, yield, and other throughput. All these different types of data at the different levels, all in the same model. That's multivariate data. That's very, very powerful. Also, it's very, very powerful and useful for nonlinear stochastic system, highly interactive systems. That's very difficult for DOE to deal with. Right? And also, it's very useful when you have multi-layers of interactions. You know, one moving part affects another moving part, which affect the outcome. And we do not know before we do the analysis whether there is even a interaction or correlation. And the machine learning model can tell us that, right? Another very important attribute is it's dealing with real-time data. It's working with the machine as the machine is running. Right? And you know, for us to do DOE, that's just impossible to handle. So it's a dynamic, very low latency and dynamic. It's building a model with the ongoing real-time condition. Right? And further with that prediction, can do a dynamic control, can tell the machine to do certain things, going to autonomous. So because of that, the more I learn about machine learning, and more I realize the power of machine learning, way beyond what I was able to do or expect from DOE. So machine learning, there have been a lot of applications in the industry, supply chain management, NPI, production planning. But today, the use cases I'm going to introduce are going to be related to traceability, predictive maintenance, throughput and cycle time, as well as process and yield improvement. Okay. So if you look at the industry, you know, SAMI and other organizations, they all have a smart manufacturing initiative, right? So basically they find the pillars of smart manufacturing as, you know, sensing, connecting, and predicting. And the different companies, enterprises may mature through different levels of maturity, from reactive to preventive to predictive. Predictive is already quite advanced, but finally to autonomous. And I'm hoping to illustrate through the use cases, I'm going to share that, you know, this all can be done in one platform. Because we recognize that the industry has many demands, and we have certain tools already in the industry that give us the smart dashboards, you know, the observability, and help us manage the line level, cycle time, OEE, et cetera, right? But what the industry needs is to go even deeper, to do a predictive analytics and using that prediction for machine adaptive control. And that's what we can achieve with the right tool, right platform. So next, I'll briefly introduce the architecture very quickly. So this example I'm going to use this to illustrate how it can be done and what it can do. So in this particular platform, the foundation of this platform is data virtualization. How you get the data. Machine is running, there are many machine sensors within the machine. So here, this platform is interfacing with the machine to ingest machine sensor data, controller data, process log, ingesting that data real time, 10 milliseconds, every 10 milliseconds, 20 milliseconds. 10 milliseconds is about 100 hertz. Right? Is that frequency real time? And again, it's a multivariate data. And then once it has that data, and that is very powerful, then it does the data transformation, staging, and filtration, for cleansing, and make sure that data is good and ready for building machine learning models. That's a foundation of the other modules and functionalities. So once we have.
So Dongkai, just as you go through this, I think one of the common questions that I hear is how much of a data scientist does somebody need to be versus somebody familiar with the application at an engineering level. So maybe as you go through this, you could highlight,
right,
the difference there. Because yes, you need to know how the tool works, but maybe you just want to become an expert in using the tool.
Right, right. That's a good question, Ira. So I will, it's a right slide, I'll address that. Yeah. So, but here, so far we talk about, building them, developing this platform, and building machine learning itself, and developing the platform itself, that had to be by the experts, the data scientists. Using it can be by just everyday process engineers. But I will give some more details later. Right? So again, here, if you look at the architecture of the platform, you start with the data virtualization to ingest data from sensors, actuators, PLC, process logs, so different protocols, and also with the enterprise level data, line level data, site level data. Right? With all that data, and it will build the machine learning model. And once you have a machine learning model, there are a lot of things you can do. One of the things you can do is anomaly detection. When I say anomaly detection, I'm not just talking about the machine. I'm talking about all the moving parts within the machine. We illustrate more next. Right? Then you can do process optimization. Which motions within the machine are affecting a particular outcome, alignment accuracy or epoxy error or something else. That type of machine learning model. Do predictions. And you do predictions, and the prediction can give you a lot of insights, recommendations, and you can act on. Right? Then once you have confidence in that model, and you run it for a few weeks, and then you can let that work with the machine control directly. That's called adaptive control. The machine can run autonomous. But that's not the first step. That's like after a few steps. You have confidence, you're comfortable with that prediction. Right? So it's a fully integrated platform. Also, it's an edge solution. It is possible because all of this is happening right there on that machine. It does not leave the machine. Of course, it can interface with the cloud, but what we talk about here is all done on the machine itself. It's an edge solution, so it's a low latency. Okay, so but I want to spend more time talking about the applications, right? So how is this? How this deployed? Okay, so here we're looking at a machine, and we all know there are many moving parts, sub-assemblies within the machine, and there could be a goniometer, could be some other sensor, a gripper, a conveyor, or something, right? And the machine already has a lot of data. Machine has sensors. Right? So the software is interfacing the machine to ingest the data that's already there. And again, 10 millisecond interval, 20 millisecond interval, right? So ingest all that data, and synchronize that data in a time series, a time sequence, and so it can be useful. Then from there, build a machine learning models for various applications. So the machine just run, a machine does not have to stop. The machine just keeps running. The machine does whatever it does. Then that can be used for predictive maintenance. I'll explain next. Then for control, predictive control, so you do one step more. That is, based on your prediction, your machine learning model prediction. Once you have a confidence in that prediction, you can have the software platform interface with machine control directly. I'll give an example later on. So you can tell them different parts within the machine, to move faster, more slowly, rotate this way, that way. That's adaptive control. So the machine can go autonomous. So, but that's the highest level. That does not happen right away because we need to optimize the model. We need to build the confidence in the model. Then we go to that step. And you don't have to go all the way. You can go step by step. And also because this platform is machine agnostic, it can be deployed to different machines on the line. And the benefit of that is that not only you are optimizing each individual machine, here you can also utilize the data from a previous step to optimize the downstream process. And so that is also very powerful. Right? So the steps are optimized together in an integrated way. And I'm sure we can all see that the power of that capability. So a few examples, use cases. I'm using this example just for illustration purposes. Okay, I'm restricted to share certain details, certain specifics, but I think they are adequate for getting the message across. But if some colleagues are interested in more details, we can talk offline. But generally, the use cases as examples, right, can be for predictive maintenance. For this can be for the front end of the process, can be for back end of the process, can be for semiconductor manufacturing, or can be for packaging. Right? So predictive maintenance and can be for predictive optimization. That's process optimization. Can we optimize a fiber alignment process or die bonding process? Right? Then adaptive control we talked about earlier, right? To have it go autonomous. There can be other examples, other use cases that can be developed. So here are a few use cases as examples for illustration purposes only. Here's a unit level traceability, right? So because the model can ingest machine data, when I say machine data, I'm referring to the machine moving parts or moving or non-moving parts. Right? Because it can ingest machine data real time, so we get a lot of data, the state of the machine at any given time, again, millisecond interval. So when we talk about unit level traceability, I mean, we all have to do traceability in our factories, right? But here it goes that deep into the machine. Not just, we do a 2D barcode, we know this board or this die is from that lot of production. It goes into the machine, say what parameters of the moving parts within the machine are used for that process step to build this unit. And that is very useful because once it's very useful for diagnostics. If later on we identify some issue, want to go back and see what happened, information is there. That level of details. Right? Then it's also very useful to look into the machine. So where is my bottleneck? Which process step? Which motion is the bottleneck for my process? We have all known, learned about lean manufacturing, looking at the bottleneck within a line, which machine is the bottleneck. But here's looking into the machine, which motion is the bottleneck for that process step, because you have this information now. Right? So traceability, and similarly for observability, okay? Of course, we can do the machine level and the line level, there's semi-standard for machine availability, and all that can be done. But we can go even deeper, really unprecedented level of granularity, give that level insights about the state of the machine at any given time. So that is very powerful. We can do a lot of things with that information, with that insights. Then, excuse me. Another use case I'm sure most of people will be very interested in is predictive maintenance, right? So we have been, there have been a lot of discussion about preventive maintenance, then predictive maintenance. But preventive maintenance often, either you do it too early or do it too late. And if you do it too early, you're wasting your resources. But can we do predictive maintenance, meaning we know ahead of time which part of the machine is having a problem, is deteriorating. That's what this module, this functionality will do. That is because it's monitoring the machine, the different parts within the machine. It's ingesting high frequency data, real-time detection. So with that data, and also it's referencing the contextual data in the process logs, right? In the same model. So with that data, the machine can build the model for normal state for, say here, a gripper. What's a normal state? This is unsupervised learning because the algorithm is identifying the pattern. Once it's established in normal state, then of course, as the machine runs, it can identify abnormal situations. That's anomaly detection. So basically what it does is, it's the way before any machine part breaks down, it's already detecting some anomaly, some deterioration, and can give early warning, early alerts to an operator or process engineer, along with guidelines. So if some machine part is deteriorating, here's what you can do. Of course, we work with the process engineers to develop these recommendations as a menu. But the machine learning model, the anomaly detection enable the process engineer to do that. So this is way before any machine component part breaks down, and you have to shut down the machine, shut down the line, get a replacement part, and it gives that early. That's what we call predictive maintenance. Then another very important application is process optimization. So here example, transceiver. And we have links attached, transmitter, receiver, and there are many process steps for each of these stations, right? And then there are several motions for each process step. We're all familiar with that. And so machine learning model can be built for each of these motions. And with that, for example, a fiber alignment, we know there's die attach, links attach, aligning the fiber, and then epoxy dispension the cure, 6-degree freedom, right? Align the fiber with the photonic IC. And at a typical active alignment, you start with a certain position, you move XYZ, RX, RY, RZ until your optical output power is within certain spec, certain range, as determined by the goodness of fate. And there are a lot of data that you can capture. UV power bonding head position and other force sensor speed, etc., right? So in this particular example, in a typical active alignment, so in this particular case, it takes 32 seconds because it's a very low through process. You do all the 6 axes, but they may interact with each other. But in this model, it utilizes the data from previous historically accurate successful alignment and use that data on the run to predict what is the best starting position to get to that final optimum position for the optical power output. And because that model, it reduces cycle time from 32 seconds to 17 seconds, almost 50% reduction. Because now you start with a position that's already very close to your desired position based on your prediction. And also it's a real time based because it's only using the previous 10 or 20 successful alignments. Right? As conditions change, it updates, it's dynamic. And so because of this, a lot of benefits I'm not going to go through, cycle time reduction, yield improvement, downtime reduction, increase machine utilization, et cetera, et cetera. And other examples, epoxy dispensing. We all deal with epoxy dispensing in semiconductor, in fiber optics and other applications, right? LiDAR and others. And there's a spec for epoxy area, there's a spec for bond line thickness, right? But there are corner cases, and we can do SPC with these two parameters, but there are corner cases where epoxy area is within spec, bond line thickness is also within spec, but the ratio of the two can cause a problem. So that means my control limit has to be dynamic real time because my epoxy area is changing. So here I can do the dynamic SPC as well. So other example, jerk setting, for example, when the machine leaves the factory, often it have a universal generic jerk setting. Jerk, as we know, it's the third derivative of position relative to with regard to time, right? So can we do a faster jerk setting so the machine can move faster? But the problem is you move faster, it's going to cause some problem in alignment or other attributes, right? So here, the machine learning model, because it's doing the machine learning model real time, it can identify what is the best, maybe a higher jerk setting for that next motion, particular motion that will not cause a problem, will still make your performance within spec. So it's like, the way I see it is like you are fine-tuning your car as you drive it, right? So the machine really can get to its best, most optimized performance real time as it runs. And so because of that, you still meet your performance requirements, but with a higher throughput because now you can run the motions faster. Okay, so we have to go faster here because we're running out of time now. Another one I just mentioned here is for test because in manufacturing setting you have many inspection steps and test steps, right? And so machine learning can be utilized to streamline test. For example, you can use the upstream inspection and the test data to simplify and streamline downstream test and inspection. So that's another potential application. Okay, so how can this be deployed? How long does it take to deploy, right? So again, this for illustration, just an example, and different systems can be different, different applications can be different. But typically, to interface the software platform with a machine, that's just within 1 day and can be done remotely, right? And the machine does not have to stop because it's all software. And it's an edge solution, works right there with the machine itself. And then, once it gets interfaced with the machine, it's start ingesting data. And then the data scientist will work on building the machine learning model. But of course, it's not building machine learning model all from scratch. There's a library of existing models for different motions that can be leveraged. And so in 2 weeks, there'll be an initial machine learning model for the a particular situation for the machine. And we call pain points or use cases for a particular machine. 2 weeks, there'll be an initial machine learning model, and we'll review with a process engineer. And then in 4 weeks, the model will be optimized. And at that time, you can already utilize in the model, utilizing the prediction for the model. But we'll let it run for another few weeks, just for just run the volume. Make sure we have the confidence, we have the comfort, and also that, Arrow, to address your earlier question, that the process engineers on the line can run on their own. So that is where the process engineer will be involved in reviewing the outcome, review the predictions, and also they can take over and run for production. Okay, so that is my presentation. So to summarize, I would say we all know that advanced packaging today requires very complex processes with increasing demand, very challenging processes, including alignment and other process requirements. And so yield is very important, but challenging. Right? Also, because of capacity, because of machine cost, throughput, cycle time are also very important. So how can we achieve the process requirements with high throughput? And that's the challenge, especially as we introduce new technologies into the industry. But this can be helped with machine learning and AI. And I hope I have illustrated that machine learning and AI can be very effective in optimizing the machine performance and also optimizing the process for advanced packaging. Can be for better alignment accuracy, or can be for shorter cycle time, and so on. And then there are other benefits, predictive maintenance, traceability, observability, et cetera, with deep insights into the machine itself. Not only the machine top level, but into the machine. Also, it's an edge solution, data security. It does not have to leave the machine. It can interface with the cloud for other purposes, but all this can be done just on the machine, right? So data security, low latency. Also, it's a machine agnostic. And also mention, Arrow, to answer your question, it's a no-code, low-code environment. So you do not have to be a data scientist to run it in production, right? And also it's scalable because it's a machine agnostic, can be used for different machines. Also, you can integrate your data with other data, IT data, so it's scalable. Okay, so that concludes my presentation, Ira. So we have time for a couple of questions, maybe.
Great, fantastic. Thank you, Dongkai. Great presentation. I had a few questions, and I'll ask them while I'm waiting to see what else the audience would like to know. So, if you're doing this at the edge, it requires compute power. Right. So, do you have to either add a server into the tool, or is there enough processing power in the existing control systems? I mean, where do you get the processing power, and what's sort of the level of processing power you need at each tool to do this?
All right, that's a great question. So the computing power it requires in terms of hardware, right? We typically, in this case, we typically will use a Intel NUC. You probably have heard. It's like, I don't know, $500, $750, whatever, a small form factor computer. That level of power, computer power. And you know, either the customer, the company has that, or it comes with a Intel NUC for that.
So then the NUC gets installed in the system, and you either have to get the data out of its existing controller, or you have to interface to the sensors that are of interest.
Right. So it will interface with that machine.
Okay.
Yeah.
Got it. All right. And so following up with that, since you said it's edge and the data doesn't leave the machine, how do you, you can optimize the machine, but can you look, let's say, across a fleet of bonding equipment? I mean, how do you get the synergy of knowing that this machine is not behaving as well as the other ones?
Right. Okay. So when I say it does not leave, it does not have to leave the machine. You know, this for this particular machine, because if you look at some other platforms, it's a cloud tool.
Right.
All the machine learning model, data processing happens in the cloud, right? Versus this one, it happens right there on the machine for that particular machine. You can integrate with your cloud. And for line level or enterprise level application, you can integrate with your MES system others, but it does not have to just for that particular machine. And many of the actions just stay there on the machine, but the top level data can be integrated with the cloud and share this. I mean, that's up to you.
Got it. Okay, and so we do have a question from the audience here, and it's related to the data ingestion. I mean, the data ingestion appears intensive on the equipment sensor side. How much automation is required on the output analysis side, measuring device alignment, die attach, coverage, etc., in order to take advantage of the ML AI? For example, measuring die attach alignment may have to take place on separate measurement equipment, not necessarily integrated with a die attach system. So now you've got one tool doing the work, and then let's say you have to go to a metrology tool to know how well it did. So how do you make that connection?
So what I have experienced, I understand the question. It's a valid question, okay? But what I have experienced in myself, and other people may have a different experience, the machines, many sophisticated machines already have a lot of data already. It has the machine already know the position of the die because it's doing active alignment already, right? And so most of the time we are utilizing the existing data, but there will be occasion where the machine does not have that data, and there need to be additional measurement, but that's not what this software will do, because the software is just doing the machine learning. It's utilizing available data, but fortunately, if you look at the machines today, I have worked with a number of machine suppliers. There's already a lot of data there.
So okay, so because it's edge, and so if it's a self-contained, let's say, work cell that does something and can make measurements as to how well it does, it's easier to implement versus having to close the loop with a downstream process.
I think in terms of machine learning itself, I mean, it's about the same. But of course, if you want to work on the entire line, it takes more integration and coordination. For sure. Yeah.
Okay. And you're using examples, let's say active alignment at chip scale. What if we go up in scale, like surface mount? Placing package parts on a printed circuit board. Is the same technology appropriate, or?
Right. I mean, because this is software, right? It's machine agnostic. So the platform can be used for whatever process. I mean, it does not have to be electronics even. Just that, of course, you need the process expertise to develop applications, but fundamentally, it can be for any machine or any product. Does not even have to be machine. Can be like, other types of data. But for application, we certainly need the application-specific expertise. And here, semiconductor packaging, and can be for electronics manufacturing, can be for the front end, SMT pick place machine. For example, nozzle pickup rate optimization, right? Or maybe it's for cycle time reduction, increased throughput, right? Or can be for backend, robotics assembly. Most of the time, or could be for AOI, for example, we can look at the X-ray machine and predictive maintenance. Some projector often fails, that causes a lot of problems. And how can we know, before it breaks down, way before it breaks down? So the predictive maintenance can be for any machine. Then the process optimization, of course, we have to have the subject matter expertise working with subject matter experts, process engineers, operators on the line, and to develop specific applications for that particular process. And so their expertise would be very valuable there as well. But it can be used for semiconductor packaging, or can be used for the fab process as well, and can be for SMT, or can be for backend assembly, and I think can be used for test process as well. I know you have a great interest in test, right. And complex test processes. It can be utilized there as well.
And we did talk about a little bit about that at last week's data and test workshop. So right. Definitely there's a lot of interest in applying machine learning and to the test process to make it more optimal, and the complexity is going up substantially. So I've got one last question, and we'll see if anything else pops in from the audience. But how does this, you talked about being edge. I mean, how does this interface to, because there's a myriad of factory floor systems, MES, ERP, the CEMIX, OEE monitoring. Where does it fit, or how does it connect, or?
Right. So if you look at the interface, there is, I would say downstream and upstream. What I mean is, number one, even if you look at the machine itself has several, different companies use different protocols. Machine sensor and PLC. And so within the machine, there are different protocols. And, we are able to, this platform is able to interface with the most common protocols within the machine itself. And that is very important, right? Because if you don't have that ability, it can be a problem, because there's so many protocols even within the machine communication, right? Then up the line, can we interface with, factory IT system, MES system, and that's probably easier. And I'm not an expert in that, but from what I have seen, IT people can figure that one out fairly easily, because basically at that level you are looking at machine level data, right? Machine performance, machine uptime, cycle time, yield, and so that can be fairly easily integrated with existing IT systems, MES systems, other systems. My understanding is that's not a problem, but to be able to communicate, ingest the data from the machine sensors and the PLC and through the various protocols that different machine builders use, historically, especially, the brownfield applications, that can be a challenging process. And but this platform can interface with the most common platforms in the machine.
Great. Well, thank you, Dongkai. I don't see any more questions at the moment, but your email address is up there, so I would encourage people who have questions to reach out to you and talk about how this may be of interest in their operations. So thank you very much, Dongkai.
Thank you, Ira. Thank you, everyone.
So just a reminder, our next Semiconductor Industry Speaker Series event will be our holiday hangout on December 15th. We will get the registration link up on the MEPTEC.org website shortly, and we'll certainly send it out via email, and it'll start at 11:30. Please drop in and say hello. Be nice to talk to everybody as we move into the end of the year. So December 15th, look forward to talking to people then. And with that, I will wish everybody a good rest of your day and look forward to seeing you at a future Semiconductor Industry Speaker Series. Thank you.